refraction. This is also why bubbles are all rainbowy. Let me show you the diagram. I'm going to walk you through the diagram before I give you the slide. It works like this. So let's make a thin film of soap. There's some soap. And here's some air. And here's some air. Okay. So this is the edge of a soap bubble. So what happens is light comes in, and it strikes a medium. It strikes a medium boundary. Now, air and soap are not the same density. So when light energy or any wave energy strikes a new boundary, what happens? Changes speed. Some energy gets reflected. Some energy gets transmitted. It's the same for sound. The bigger the difference in densities, the more energy gets reflected when the more versus transmitted. Okay? So no difference in density, all the energy gets transmitted. Huge difference in density, all the energy gets reflected. So soap is more dense than air. I'm just going to throw a little number up here. I'm going to say it's N equals 1.33 because that's the density of water. And air is 1.0. Okay, so far so good? So what happens to that wave of light? Well, the answer is two things. Part of that wave energy gets transmitted, and part of that wave energy gets reflected. Here comes the wave, and it hits it. Part of it gets transmitted, and part of it gets reflected. See what just happened? Yeah. So now you have two waves that are overlapping each other. When you have two waves that overlap each other, what do you get? Starts with an I.
Interference.
Interference. Only it's not sound interference, it's light interference. So the colors get all wonky. And then, when the light gets to the other end of the boundary, guess what happens again? Some light energy gets transmitted, and some light energy gets reflected. And it keeps going. So that's where you get the wonky rainbow patterns, because some energy, every time it strikes a boundary, some energy is getting transmitted, some energy is getting reflected, and those reflected beams overlap each other. This is what you see. And film interference. I'm not going to ask you to calculate how thick a thin film would have to be in order for this to happen. There is a formula, and I'll wait if you want to take optics in your junior year in college. You can learn all about that formula. Just realize that it has to be thick. Oil on water thin, soap bubble thin. You know where else they use this idea? Anyone have anti-glare coverings on your glasses? Yeah, so do I. There's a big chunk missing right there. It's like, oh, what is that? What's the anti-glare covering? They use the anti-glare covering. They use this phenomenon to keep glare from reflecting off your glasses. The light goes in, it doesn't come in. And by the way, the reason that soap bubbles look all rainbowy and not just one color, anyone know why bubbles look like their rainbows are moving around inside? It's a very simple idea. You just probably never thought about it before. Because the soap is, exactly, the soap is moving. There's more soap on the bottom of the bubble than on the top of the bubble, and the soap is constantly falling to the bottom of the bubble. So the thickness is constantly changing. It's thinner on top and thicker on the bottom. And as the bubble cruises along, it's constantly changing its thickness, so that's why the rainbows are constantly moving. Okay, shall we move on? No. What is everybody's favorite phenomenon in optics that now you know actually has to do with thin film interference. Bubbles. Even more than bubbles. Sometimes I see them and it makes me cry. A rainbow! Yeah.
First thing with that.
So, so basically what happens with the rainbow is, well, basically the same idea. Water droplets act as a gigantic prism. Light comes in, some of it gets reflected at the front of the droplet, some of it gets reflected at the back of the droplet, and then that light's what's called dispersed. It's dispersed into its wavelengths. Rainbows aren't really bows, by the way. They're circles. They're chunks of circles. Anyone ever seen a rain circle before?
Did you see it from an airplane?
Yeah, in order to see a rain circle, you have to have light behind you, and then the prism in front of you. So if you happen to be on a window seat in an airplane, and in the morning, if you're going north, the light's going to be on the east side. You want to sit on the west side to see it. And usually see it as you fly through the clouds. Light will go across the plane, through the cloud, and you can see it on the left side. If you're going south in the morning, then you want to flip it over. So it's basically sit on the east side. You can do it in the afternoon, but it's not as, for some reason, it's harder to see them in the afternoon. But usually see them in the morning. So light's on that side, and you're going to see it on that side. So next time you're flying, if you're flying in the morning, be on the opposite side of the light. So if the light's on the east side, you have to sit on the west side if you're going north. People used to ask me if I liked Pink Floyd. The answer is no, not really. But it's a pretty good diagram of a Newton's prism. That's called Newton's prism. I don't know why it's called Newton's prism. It's called Newton's prism. Light's bending more in the purple than in the red. It's got further to travel. Okay. Shall we move on? Let's move on. All right. Diagramming. You're going to need a 3 colored pencils. So grab yourself 3 colored pencils. Actually, I'm going to make this easier rather than you all getting up. Ray diagramming. I'm just going to throw a whole bunch of colored pencils at you. And I don't know if they're sharp or not. There you go. Right here. So some for you, some for you, some for you. You don't have to use them. You can use colored pens if you want.
Oh, so we got
All right. Great dice. Oh, you need a ruler too. I'm sorry. You need a straight edge as well. Let me get you a straight edge. I use like, I'll take her. You need a straight edge too, because we're going to be drawing a bunch of parallel lines. is super fun. All right, so a couple ground rules for doing wave diagramming. And I hate this. I really hate this, and how all animations seem to do this. They tend to bounce rays on the actual device. We don't want to do that. We want to bounce all the rays at a line that is perpendicular to the principal axis. We want to create a normal on our diagram. I'll show you what I mean by that in just a second. I'm trying to get this thing squared away. Okay. So, we're not going to bend the rays at the actual device. We're going to create a normal on the device to make it easier to do our math. So, draw a vertical line through the device. That's going to represent your mirror. Now, it looks like a flat mirror, but it's not a flat mirror. Again, a lot of animations, they draw it through they bend the ray at the device. The problem with that is when you get the lenses, it becomes a huge issue. We don't want to do that. So we don't want to get in the habit of doing that. We want to bend them at a line that is perpendicular to, perpendicular to the normal. Wow. This is just peaches. Let's try that again. That's straight. That's straight by you, is that straight? Yeah. Okay. I'm going to redraw my normal here. All right, so to determine the image location, we need a focal distance and an object location. We need a focal distance and an object location. And we're going to use that information to draw 3 lines. And if we did it right, then those 3 lines are going to come together at an image location. So, our first ray, parallel, then focal. So, get your favorite first color. I'm going to make it green. My first color is going to be green. And our first ray is going to go parallel, strike the normal, and bounce to the focal. Are you ready? So I'm going to run in a parallel line. It's going to hit the normal, then I'm going to draw it through the focal distance, like so. And I make a little arrow to say that's what happened. So that's ray number 1.
What?
Parallel, then focal. So I made a parallel line, parallel to the principal axis. It struck the normal, then came down through the focal point. Okay. Give me a thumbs up, you got your first line done. So you're supposed to. Okay, good. Maybe we'll do this for a while.
For the, is it right there?
Yeah, those are the 3 rays. Second ray, get your next color ready to go. I'm going to use red. And your second ray does exactly the opposite. It runs through the focal, but it still bounces at the normal. So you go through the focal, but it still bounces at the normal. I hit the normal, so I aimed it through the focal point. It struck the normal, and then I reflected it parallel. So the first one is parallel then focal. The second ray is focal then parallel. There we go. So first ray, parallel, then focal, second ray, focal, then parallel. Now, it should look like, to us, that these two rays interact right there. So there's a very good chance that's where our image is. The third ray is a check ray. And it's really easy if you have your C. In this case, we're going to actually need to measure our C. Your third ray runs through the center of the curvature. So what I'm going to need to do is I'm going to need to measure my focal distance and double it to get my center of curvature. I measure the focal distance and I double it to get the radius of curvature. If I have a mirror and I have a radius of curvature, I half it to get the focal distance. If I have focal distance, I double it to get the radius of curvature. In this worksheet, the focal distance is given to us, but not the radius of curvature. So we're going to need to double it to get the radius of curvature. Okay. Furrowed brows, how can I help? Okay.
I still don't understand how you get it.
Okay, so in a mirror has a radius of curvature because, like, imagine a whole bunch of these mirrors where the mirror got bigger, bigger, bigger. The radius of curvature is going to be about right here. So every point to the mirror is the same from the radius of curvature. The focal distance of a mirror is 1/2 the radius of curvature. So if I halve the focal distance, F, I double it to get C.
Oh, so you just take F of the mirror and then double it to the side.
Exactly. For me, I had 9 centimeters, and I just made that 18 centimeters. Yours is going to be considerably smaller.
Oh.
So I just measured the distance of F to the normal and doubled it to get C. So our third ray is a check ray. I'm going to make my check ray blue. And the third ray just runs through the center of curvature.
Should we be careful extending it into that second part Ferrari?
Probably.
Yeah.
Yeah. I'm going to erase mine. Yeah, probably that would be a good idea. I wanted to maximize paper usage, but you're going to have overlap when you do these worksheets. All right. So where your rays come together, your first 2 rays give you the image, your third ray gives you a check. If your third ray doesn't hit your image, then you did something wrong with the first 2 rays.
So that point, what is that point? The focal point?
Through the center of curvature. So you go parallel, bounce it at the normal, through the focal point. Second ray, through the focal point, bounce it at the normal. Third ray, through the center of
To
curvature.
find what? But what are we finding?
The image, where the image would be.
Oh.
So if you had an illuminated object here, your image is going to be here.
So the focal point is the line, not the curve.
The focal point is a dot. A dot on the principal axis.
Okay, why did we do the line instead of just the curve?
Because I didn't want to bend the rays at the device itself. I wanted to give us a common bending line. So rather than actually strike the line, like you can see how the lines strike the device itself. They go parallel, focal, focal, parallel. This only works for mirrors, it doesn't work for lenses. So I want to get us in the habit of basically making a normal and always bending
But
it
it
at
will
normal.
always work if we draw that line.
Yes.
Okay.
Yeah. So again, first ray, parallel, focal, second ray, focal, parallel, third ray, check through the center of curvature. All right, now that we've drawn our image, so give me a thumbs up if you drew an image and it looks kind of like mine. Cool. All right, now that we drew the image, we can collect information about this image. The distance from the object to the normal is DO. So the distance from the object to the normal is DO. The distance from the normal to the image is DI. The height of the object is O, and the height of the image is
Hi.
Wait, repeat that?
the height of the image is HO, H sub O, and the height of the image, sorry, the height of the object is H sub O, and the height of the image is H sub I. We've got a whole bunch of information.
That wouldn't necessarily be a negative value, would it?
The height?
DI?
Yes, it is.
Really?
Always?
Yes. When it's pointing down, yes. This is why the magnification is given to you at negative DI, DO, and HO. So we basically have a negative magnification in this case.
Can you go over that just one more time?
Sure.
Everything.
Okay, so the distance from the object on the principal axis from the object to the normal is DO.
Yeah.
The distance from the normal to the image is DI. The height from the principal axis to the top of the object is HO, and the height from the principal axis to the bottom of the image is HI.
Okay.
And there you go. So we can address some numbers and some words. Each image gets 3 words. So the image is either real or virtual. It's either magnified or reduced. And it's either upright or inverted. So let's pick what my what our image is. Is it real or virtual?
Real.
Real.
Exactly, it's real. Because in a mirror, this is the real side, this is the virtual side. Is it magnified or reduced?
Magnified.
Isn't it reduced?
It's reduced. I know it's reduced because magnification is negative DI over DO. And your DI is smaller than your DO. Magnification is DI over DO equals HI over HO. Since I know my DI is smaller than my DO, my HI has to be smaller than my HO. So it is reduced. And is it upright or inverted?
Inverted.
Inverted, it's upside down.
How do you know that?
It's pointing down.
What's pointing down? It's a negative
How do you determine M? I mean, I see the equation there, but then it asks in the directions to determine the DI, HI, and M.
Measure.
Do we need, okay, so you do want a real value for that?
Yeah.
I don't really know the difference between magnified and reduced.
Magnified is bigger. Reduced is smaller.
How do you tell?
Okay, so the easy way to tell is to just measure it. Measure that to measure this.
Okay.
But you can also check and realize that the DO is larger than the DI. So this fraction is going to be less than 1.
So then it's reduced.
Yes.
Okay.
Magnification is less than 1. Okay, so don't have a lot of time left, so we're going to pick this up again Thursday after our lab. I don't think you really even, yeah, everything is practice, so you don't really need to do the pretty beautiful. If you could please return your colored pencils and your rulers, the boxes up front, that'd be really great.